Welcome back to The Explainer. Okay, today we are taking a notoriously dense, kind of intimidating programming topic, and honestly, we're going to break it down until it's crystal clear. We're talking about polymorphism in Java. Look, if you're prepping for a software engineering interview, or maybe you just genuinely want to understand the actual pillars of object-oriented programming, this explainer is absolutely your goldmine. I'm so pumped to get into this because we're going to demystify polymorphism from absolute scratch all the way up to an advanced industry-level design perspective. Let's just jump right in.
So here's our roadmap for today. 1. Polymorphism, the core concept. 2. Compile-time polymorphism, also known as static. 3. Runtime polymorphism, or dynamic. 4. Upcasting and dynamic dispatch. And finally, 5. The dangers of downcasting.
All right, Section 1, Polymorphism, the core concept.
You know, the word itself actually gives away its entire secret right off the bat. Poly literally means many, and morphs means forms. So putting it together, it's a single entity functioning in completely different ways based on the condition or the exact object it's acting upon. In the programming world, this basically means a single function or a method or an operator can have entirely different behaviors depending purely on the input you feed it. It's wild.
And this brilliantly illustrates the concept in the real world. Think about this Rahul analogy for a second. Rahul is just one guy, right? He's got one name, but look at all his different forms. To his parents, his form is a son. To his wife, his form is a husband. To his kid, he's a parent. To his company, he's an employee. The entity, Rahul, is exactly the same person, but his behavior, his daily responsibilities, how he interacts, all of that changes completely depending on his environment and context. And really, that is polymorphism in a nutshell.
Moving on to Section 2, Compile-time polymorphism, which we also call static polymorphism.
Now, what's really interesting here is how Java actually explicitly restricts us, especially if you compare it to other languages like C++. We've got two primary concepts here, method overloading and operator overloading. Java wholeheartedly supports method overloading. That means you can have multiple methods with the exact same name sitting right there in the exact same class. But operator overloading, yeah, Java says a hard no to that. You, as a developer, absolutely cannot redefine what a plus sign does to your custom objects. Now sure, Java internally overloads the plus operator, so we can easily concatenate strings, but user-defined operator overloading, that is strictly blocked. So we really just have to stick entirely to method overloading.
So how do we actually pull this off in code? Let's walk through the steps to build an overloaded add method for a calculator. Step 1, you just use the identical method name, like add. Step 2, you change the argument count. So you can have one add method that takes 2 integers, and then another completely separate add that takes 3. Or step 3, you change the argument type. You could even have an add method that takes 3 integers and, say, 1 double. Calling back to our Rahul analogy from earlier, the method name add stays exactly the same, but it naturally morphs to handle whatever specific data type or count you decide to pass into it.
Okay, so the absolutely crucial takeaway here is that static polymorphism decides everything during the compilation phase, right when that bytecode is generated. The Java compiler basically looks at your arguments, finds a matching method, and locks it in. Done. But that begs a pretty fascinating question. What happens when the decision just can't be made in advance? Like, what if the decision has to happen at runtime?
Well, that brings us to Section 3, Runtime polymorphism, or dynamic. This is where the real magic happens. Let's introduce method overriding by comparing these two classes. We start with a parent class, let's call it shape, that has a very generic draw method. If you call it, it might just print something boring like drawing generic shape. But then, we inherit from that parent to create a child class, like a circle. Now, you obviously don't draw a perfect circle the same way you'd draw a generic, undefined blob, right? You'd probably need a compass or something. So the circle class provides its own specific, overridden implementation of that draw method. The method name is completely identical to the parent's, but the child basically refuses that generic behavior and executes its own highly specific logic instead.
Let's build on that in Section 4, upcasting and dynamic dispatch. The absolute aha moment here is dynamic method dispatch. Let's break this down. Imagine our reference variable type is always a generic parent, like shape S, but the instantiated object it actually holds dynamically changes. If that shape S is assigned a new circle, Java is smart enough to execute circle.draw. If it holds a new rectangle, it executes rectangle.draw. So the variable holding the object is totally generic, but Java dynamically dispatches the exact right method based on the specific child object it actually holds in memory at that exact moment. It's brilliant.
I really want to emphasize this next point because it is a core industry-level takeaway. Parent can hold the child and call the relevant method. Just think about what this means for your codebase. You don't have to write hundreds of redundant, slightly different functions, draw a circle, draw a rectangle, draw a triangle. No way. You simply write one single function that accepts a generic shape, and because of upcasting, that parent reference gracefully holds the child and dynamically triggers the correct behavior every single time. It makes your systems incredibly clean, scalable, and just so much easier to maintain.
But hey, since we've successfully pushed a specific child into a generic parent reference, you might logically be wondering about the reverse, right? If upcasting works so beautifully, what about downcasting? Like, can we actually go backward?
Which leads us perfectly into Section 5, the dangers of downcasting.
Time for a bit of a reality check. Let's trace the flow and, honestly, the severe risk of doing this. Downcasting is essentially the concept of forcing a generic parent reference back down into a specific child type. Let's say you cast a generic shape reference down to a circle because, for whatever reason, you desperately want to call a personal method that only exists inside that specific circle class. Well, here is the massive danger with that. What if at runtime that generic shape was actually holding a rectangle object? Your IDE, your code editor, they will not catch this. It just assumes you know exactly what you're doing. But the result? A fatal class cast exception that literally instantly crashes your entire program right at runtime. This is exactly why senior developers avoid downcasting whenever possible. It entirely breaks that elegant generic safety net we just spent all that time building with upcasting.
Man, we have covered some truly incredible ground today. From raw holes changing forms all the way to the intricate, hidden mechanics of dynamic method dispatch. Really understanding these concepts, that's what separates everyday coders from true software architects. So I'll leave you with this final thought. With great power comes great responsibility. Which form of polymorphism is going to shape your next project? Are you going to strictly define boundaries with compile time overloading, or are you going to build incredibly flexible architectures using upcasting? Definitely keep these concepts front of mind for your next coding interview or major system design. Thank you so much for joining me on The Explainer. Keep learning, keep coding, and I'll catch you on the next one.